In 1962, John Glenn was about to become the first American to orbit the Earth. NASA had a brand new IBM 7090 mainframe computing his trajectory. The machine had been checked. The code had been verified. Glenn didn't trust it. "Get the girl to check the numbers," he said. "If she says the numbers are good, I'm ready to go." The girl was Katherine Johnson. She was 43 years old. She had been doing orbital mechanics by hand for nearly a decade. And the numbers she checked that day would determine whether John Glenn came home alive. So what exactly was Katherine Johnson calculating? Orbital mechanics. The mathematics of how objects move when gravity is the only force acting on them. And gravity is always acting. An orbit isn't a thing floating in space. It's a thing perpetually falling and perpetually missing. Isaac Newton figured this out in 1687. Fire a cannonball from a mountaintop. Fire it faster, it goes further before hitting the ground. Fire it fast enough, and the curvature of its fall matches the curvature of the Earth. It never lands. It just keeps falling. The moon falls toward the Earth. The Earth falls toward the sun. Everything falls. The trick is falling sideways fast enough that the ground curves away beneath you. That's an orbit. And describing one precisely requires solving a differential equation. Newton's law of universal gravitation says the force between two masses equals g times m1 times m2 divided by r squared. G is the gravitational constant, a number so small it takes 11 decimal places to write down properly. 6.67430 times 10 to the minus 11. m1 and m2 are the two masses. R is the distance between their centers. Now combine this with Newton's second law, F equals m times a. The gravitational force on a spacecraft equals its mass times its acceleration. Rearrange, and you get the acceleration equals negative g times m divided by r squared, pointed back toward the center of the Earth. That's a differential equation. The acceleration of the spacecraft depends on its position. But its position depends on how it has been accelerating. Position determines acceleration. Acceleration determines position. This is the fundamental circularity of orbital mechanics. You can't solve it in one step, so you solve it in many tiny steps. This is numerical integration. The simplest version is Euler's method, invented by Leonhard Euler in 1768. The idea is beautifully simple. You know where the spacecraft is right now. You know its velocity right now. You can compute its acceleration right now from the gravity equation. So you step forward a tiny amount of time, delta t. New position equals old position plus velocity times delta t. New velocity equals old velocity plus acceleration times delta t. Then you recalculate the acceleration at the new position and step forward again. And again. And again. Each individual step is slightly wrong. The velocity changes during the step, but you're treating it as constant across the interval. That's an approximation. But if delta t is small enough, the error in each step is tiny, and the accumulated error stays manageable. A full orbit might require 10,000 steps. Katherine Johnson made the steps very, very small. And she computed them by hand. With a pencil, a slide rule, and reams of paper. For a single spacecraft orbiting a single planet, there's actually an exact solution. Kepler proved it in 1609. The orbit is an ellipse. Semimajor axis A, eccentricity E, and the period equals 2 pi times the square root of a cubed over gm. This is Kepler's third law. Beautiful. Clean. Exact. No numerical integration needed. But the real world isn't two bodies. The Earth isn't a perfect sphere. It's oblate, wider at the equator, which means the gravitational field isn't perfectly symmetric. The sun pulls on the spacecraft. The moon pulls on the spacecraft. The atmosphere drags on the spacecraft during re-entry. Each of these adds correction terms to the simple Keplerian ellipse. And those corrections destroy the clean analytical solution. You're back to numerical integration. Step by step. Force by force. For the Mercury missions, Katherine Johnson calculated the launch window, the trajectory, and the re-entry point. She had to account for the rotation of the Earth underneath the spacecraft. Launch from Cape Canaveral, orbit 3 times, and the landing zone has moved because the Earth has rotated nearly 70 degrees in those 4.5 hours. She had to account for the oblateness of the Earth, because the equatorial bulge shifts the orbit slightly with each revolution. This is called J2 perturbation. She had to account for atmospheric drag during re-entry, which depends on altitude, velocity, and the ballistic coefficient of the capsule. Each of these adds terms to the differential equation. More terms, more steps, more pages of arithmetic. The re-entry calculation alone filled 30 pages of algebra. She published it as NASA Technical Note D529 in 1959. Determination of azimuth angle at burnout for placing a satellite over selected Earth position. She was the first woman in the Flight Research Division to receive author credit on a research report. Her desk was covered in paper. She called it analytical geometry. Everyone else called it wizardry. Then came Apollo. Going to the moon is not a straight line. You launch into low Earth orbit at about 160 kilometers altitude. Then you perform a translunar injection burn, a precisely timed rocket firing that accelerates you from orbital velocity to escape velocity plus a bit more. This puts you on a transfer orbit, an elongated ellipse whose far end reaches the moon's orbital distance. But the moon isn't standing still. It's orbiting Earth at just over 1 kilometer per second, covering about 33,000 kilometers a day. You're not aiming at the moon. You're aiming at where the moon will be 3 days from now. At the right speed, at the right angle, the moon's gravity captures you into lunar orbit. Miss by a fraction of a degree, and you either crash into the surface or sail past into deep space. The re-entry corridor for coming home is a window about 40 kilometers tall. Too steep, you burn up. Too shallow, you skip off the atmosphere like a stone on water and drift into a solar orbit. Katherine Johnson calculated the trajectory equations for Apollo 11, the mission that landed humans on the moon. The real mathematical challenge of Apollo is the three-body problem. Earth pulls the spacecraft. The moon pulls the spacecraft. The sun pulls everything. For two gravitational bodies, Newton gave us exact solutions. For three bodies, there is no general closed-form solution. Henri Poincaré proved this in 1890, and in doing so essentially invented chaos theory. Three gravitational bodies interacting can produce trajectories so sensitive to initial conditions that predicting far into the future becomes impossible. So you don't solve it analytically. You simulate it numerically. At each time step, you compute the gravitational acceleration from every relevant body. The Earth pulls with g times m Earth divided by r Earth squared. The Moon pulls with g times m Moon divided by r Moon squared. You sum the accelerations as vectors, update the velocity, update the position, and step forward. For Apollo, the numerical integration used a Runge-Kutta method, a more sophisticated version of Euler's method that evaluates the acceleration at multiple points within each step to cancel out more of the truncation error. This is what the IBM 7090 was doing. And this is what Katherine Johnson was checking by hand. Katherine Coleman was born on the 26th of August, 1918, in White Sulphur Springs, West Virginia. She was counting everything by the age of 4. Steps to church. Plates on the table. Stars, if she could see enough of them. The local school for black children only went up to 8th grade. Her father moved the entire family 120 miles to Institute, West Virginia, so his children could attend high school. She graduated at 14. She enrolled at West Virginia State College and took every maths course they offered. The professors created new courses specifically for her. She graduated at 18, summa cum laude, with degrees in mathematics and French. In 1939, she was one of 3 black students chosen to integrate West Virginia's graduate schools. She left after 1 year to start a family. In 1953, she joined NACA, the predecessor to NASA, in the segregated West Area Computing section. A room full of women, mostly black, doing the calculations that kept rockets in the air. They were human computers. The job title was literally computer. What set Katherine Johnson apart was precision and nerve. She asked to attend the engineering briefings. Women didn't attend briefings. Is there a law against it? She asked. There wasn't. She attended. She asked questions nobody expected from someone who wasn't supposed to be in the room. Why can't a woman attend the briefing? Why not use this equation instead of that one? She wasn't confrontational. She was curious. And she was always right. Her calculations were never wrong. Not approximately right. Not close enough. Exactly right, to as many decimal places as you cared to check. In orbital mechanics, close enough means your astronaut burns up on re-entry or drifts off into space. The margin of error for re-entry angle is plus or minus 1 degree. 1 degree. The difference between coming home and not coming home. There is no rounding. There is no good enough. There is only right. On April 13, 1970, Apollo 13 was 2 days into its lunar mission when an oxygen tank in the service module exploded. The crew couldn't use the main engine. They couldn't turn around. The only option was to continue to the moon, loop around it, and use the moon's gravity to slingshot back toward Earth. This is called a free return trajectory. But the free return alone wouldn't bring them home fast enough, and the trajectory was slightly off. They needed a correction burn. A short firing of the lunar module's descent engine at precisely the right moment, at precisely the right angle, for precisely the right duration. 2 seconds too long, and they miss the re-entry corridor. 2 degrees off, and they skip off the atmosphere. Johnson worked on the emergency return trajectory. The numbers had to be right the first time. There was no second chance. Her calculations were part of what got them home. She later said that working on the contingency procedures for Apollo 13 was the work she was most proud of. Not the mission that went perfectly. The one that almost killed 3 men. Katherine Johnson received the Presidential Medal of Freedom in 2015, at 97 years old. NASA named a building after her while she was alive to see it. The Katherine G. Johnson Computational Research Facility at Langley Research Center. She passed away on the 24th of February, 2020, at 101. Every time a spacecraft reaches orbit and arrives precisely where it was supposed to arrive, it's because someone did the mathematics. Computed the forces. Stepped through the differential equations. Summed the perturbations. Checked the numbers. The same way she did it. By hand, with a pencil, in a room she wasn't supposed to be in, solving equations nobody thought she could solve. She didn't fix the moon. She fixed the path to get there.